So let's continue our discussion of applications. So in the previous class, we looked at this problem of classification. Uh, there are two classes which essentially correspond to two different subsets, disjoint subsets of Rn, and we're given points from each of these subsets. Our goal is to design a classifier which distinguishes between points from one subset and the other. Right? And we were not given the subsets themselves, but rather some random points drawn from each of these two subsets. And our goal is to essentially design a hyperplane that that partitions or that such that one of the sets is on one half space and the other on the other half space. Right. So essentially, this corresponds to predicting whether a new point seen from S1 or S2 lies has been correctly classified or not. Right. So far we've been assuming that S1 and S2, the two subsets, are separable. So no matter what happens, there exists a hyperplane that separates the two sets S1 and S2, that they are linearly separable. Right. And we saw that in general, finding a classifier is essentially the same as solving a feasibility problem. Basically, you just minimize a constant function subject to the constraints that all points coming from one subset lie on one side of the hyperplane, and all points from the other subset, that is those labeled 1, come from the other side or all lie on the other side of the hyperplane. But we can improve this. We can now ask for sort of the best hyperplane that separates points labeled 0 and points labeled 1. And through this, we looked at this class of maximum margin linear classifiers, wherein for a given classifier, we construct this buffer zone, that is all points which don't contain points from x points labeled 0 or 1 coming from the observables, our test set effectively. Right? And we want to maximize and we want to construct that linear classifier for which the margin is as large as possible, or in other words, the maximum margin linear classifier. Right? And that, as we saw, can be formulated as this convex optimization problem. It is to minimize minus t subject to the constraints that A transpose xi0 is less than or equal to b minus t, and A transpose xi1 is greater than or equal to b plus t for all I equal to 1, 2, 3 up to the number of samples that we observed labeled 0 and 1. And we also had this additional constraint that the norm of A should be less than or equal to 1. We also looked at the dual problem, and the dual problem, as we saw, had a nice interpretation as basically the midpoint. It gives you the midpoint or the distance between the convex hulls of the observed points. Right? So you look at the convex hull of all points labeled 0, the convex hull of all points labeled 1. The maximum margin linear classifier is basically the one that passes through the midpoint of these two convex hulls, right? Or midpoint of the minimum distance between the convex hulls. The maximum margin itself would be equal to the minimum distance between these two convex hulls. Right? So one can sort of just write a few lines of code to just solve this convex optimization problem using CVX_pi. Let's perhaps try to do that. Okay, so firstly we need to generate some points labeled 0 and 1. So let's assume a ground truth. Uh, Let us say that our classifier, or in other words, we want to make sure that there exists a linear classifier, right? And for maybe as an example, let us take the line x1 plus x2 equal to 1. Right? That's a line in 2 dimensions. And we'll draw points from one side of this hyperplane and points from the other side of the, let's say x is um, let me draw say 30 points uh, in R2, right? I'm randomly generating 30 points from R2, and I'll label some of these 0 and some of these 1. So let's say that x ones are those points for which, let's look at the labels. So these are 30. Equal to, so let's we label those points for which x of 0 plus x of 1 is greater than 1 with 1. What am I doing? I'm effectively drawing random points from the square of side length 1 between 0 and 1. I've drawn 30 points. This is the true partition, right? So every point on the left hand side is going to be labeled 0, and every point on the right hand side is going to be labeled 1. So x of 0 plus x of 1, if it is greater than 1, then this is labeled 1. Let me partition this. So x ones equal to y of, sorry. So all those points which are labeled 1 are going to be put into x ones. All those points which are labeled 0 are going to be put into x zeros. Okay, so let's just plot these points. I will first plot the points which are labeled ones. So x one 0. I'll also maybe plot the line x plus y equal to 1. So this is the true split, and there's one point almost on the line. All right, so this is the set of points that we have. Our goal is to find out what the maximum margin linear classifier is. The note that ultimately the classifier that we do obtain by solving the convex optimization problem may or may not be equal to this. In general, it won't. Right? So let's set up the problem. I need variables. Right? So what are the variables that I need? I need a, b, and t. So this is variable. I have b, and a is what is my objective? Minimize minus t, subject to what constraints? Yeah. A transpose x is less than or equal to b minus t. So let me see how we can do that. So a transpose into, I guess, x zeros, or I can write this as x zeros transpose a is less than or equal to x zeros. So b minus t and x ones into a should be greater than or equal to b x t. Other constraints? P dot norm a square should be less than or equal to 1. Is that it? Problem is vector constraints. This, so the optimal a turns out to be equal to 0.74. Let's see what the max margin is. Whatever is close to 0. Sorry, yeah, let's draw the line. I is what? It's b, yeah, so a x1 plus b x2 is equal to b, or in other words, x2 would be equal to b minus a x divided by a1. Sorry? That's right. So the dotted line is the true uh, line that partitions the two sets, whereas when we solve the optimization problem, what we get is this red line over here. So the two can be different, but that's fine. After all, it so happened that uh, the convex hull, so if you look at the convex hull of this set and the convex hull of this set, uh, the sort of closest points would perhaps, so you can see that the line joining these 2 points would be one face of the convex hull, whereas the line joining these 2 points would be kind of another face of the convex hull. This point would be the closest to the convex hull of the blue points. So if you can see carefully, the red line almost touches this particular orange dotted point.
Is it a single line or it's a marginal line? Kind of
Which one?
pictorial representation.
Correct.
Picture,
Yes.
shown as a strip line.
Correct.
Is it
But in this case, again, our strip is sort of too narrow. So, well, what we can instead do is generate even fewer points. So, uh, why? Yeah, I still have these points very close to each other, but that may still be fine.
multiplied by 2
The margin will be, yeah, 0.07. Perhaps. Yeah. So now you have a wider strip. We actually have a much wider strip. But of course, the classifier that we obtain is far worse than the actual uh, partition, right? But of course, if I now increase the number of points to 100, then obviously I'm going to be doing better. So all of this discussion that we had was assuming that the two classes were linearly separable. There exists a linear classifier, but that's not always guaranteed, right? Your data is not guaranteed to contain points which are nice linearly separated. That almost never happens in practice. So, so obviously we need a way to handle this. So now it's no longer a feasibility problem. If I try to construct a linear classifier, there will be points on either side of any hyperplane I try to construct. Right? That's going to happen in general. So, so what if the points are not linearly separable? So now we need a way of saying how badly our classifier is performing. Right? But we'll still use the same approach. We'll try to extend the approach that we had earlier. We still try to give a margin. Right? So suppose we have a classifier corresponding to this classifier. There is some margin, but now let's say that these are the points labeled 0. I could have points labeled 1 on this side of the hyperplane, and similarly I could have points labeled 0 on the other side of the hyperplane. Now, of course, there are different ways of constructing classifiers. Now, it's no longer the approach that you would like to use is no longer unique, right? Uh, so one commonly used approach is the following: you try to find out by what amount are you deviating from the margin. So in particular, a point labeled 0, how far is it from this margin on the other side? And similarly, how far is this one, how much is this one deviating from the margin? So that effectively corresponds to the following constraints. So let's say that this is deviating from the margin by some alpha I. Right? So each point is deviating from its corresponding margin by alpha I. Assuming that there were no deviation at all and the 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 points are linearly separable, recall that I had two different constraints for uh, for points labeled 0 and points labeled 1. But in fact, I could have used a common approach. Yes, question.
If this deviation part will come only after separation, it will come only after separation.
Which one? So let's assume that it is not separable at all. That is, it is impossible to construct for the set of points that I'm given. It is not possible to construct a linear classifier. There is no hyperplane that strictly separates these two sets of points. And that can indeed happen, right? I can have some points like this and points around this. Okay. But nevertheless, I still want to construct a linear classifier. Right? So and the kind of problem I'm interested in is where they're almost linearly separable. So most of the points can be linearly separated, but there are some points which would go on either side. Right? So let's look at the constraint that a particular point does not lie on the right side of the hyperplane. Right? So I'll use a different labeling of points, that is each. So recall that earlier yi was either 0 or 1 depending on whether it satisfied the constraint or whether it was labeled 0 or 1. But now I'll use a different labeling of -1 and 1. So again, it's just pure notational convenience. I can just relabel the points which are actually 0 with -1, and those which were 1 are left as it is. So these are my new labels. And the advantage with working with this notation is that, now let us say that I have a point A transpose xi 0 minus b. I take this particular this classifier. What can I say about the sign of A transpose xi 0 minus b? So I want a classifier for which A x less than or equal to b implies that the point is labeled, let's say, -1, and Ax greater than b means that the point is labeled +1. So if it was linearly separable and Ax minus b actually satisfies this, then effectively what could I say about yi times A xi 0 minus b? It would always be positive, right? So I could say that this is greater than or equal to my margin t, correct? So this would have been the constraint in the earlier problem, in the linearly separable case. Sorry?
What is the sources?
Sorry. No, I don't really need this 0 in here. It can be any x. Sorry? It may be. So this is my margin. Correct. So right now, if it were linearly separable, then I can say that this is not true if it is not linearly separable. Correct. If mod A is 1. If mod A is less than or equal to. You're right. So what I'm getting at is I can effectively use the following constraint if it is actually linearly separable, without imposing the constraint that mod A be equal to 1. So suppose I fix the margin to be equal to 1. This whole margin to be equal to 2, the width of this to be equal to 1. Okay, but now I need, of course, some constraint on the norm of A. I can't let it grow unbounded. But I'm going to put that in the objective function eventually. I want A to be small, the norm of A to be small, but at the same time, I want these properties to be satisfied. Right. So if it is not linearly separable, then I allow some deviation. The deviation is by an amount alpha I. So it can go alpha I amount in the opposite direction. So in the linearly separable case, my constraint would have been just this amount, right? That yi times axi minus b is greater than or equal to 1. I could have imposed this particular constraint.
So why do we fix the margin?
Effectively, it's okay. I fix the margin to be 1. I have one free variable, right? The width of the margin or the norm of A. I could say that the norm of A, I put an additional constraint, the norm of A be less than or equal to 1, and I use a margin of T, right? Right now, what I'm going to do is I'm going to fix the margin to be 1, and I'm going to minimize the norm. So these are going to be my constraints. One by norm, yes. Right? Effectively, this is the same as saying that yi times xi by A transpose xi by norm A minus B is greater than or equal to 1 by norm A minus alpha I by norm A. So in our earlier formulation, this would have basically played the role of T. Okay, any questions? So earlier my goal was to minimize minus T. Right now my goal is going to be to minimize norm A in some sense, or some function of norm A. But in addition, I also want the alpha i's to be small, right? So alpha I is the deviation from the margin. So the goal is basically to minimize norm A square, let us say. But I also want to minimize the deviations. So I'll take summation equal to 1 to the total number of points of uh, alpha j raised to some p. So for example, I could have used alpha j square, right, which would give me the 2 norms squared of the alpha vector, the vector of all deviations. But in general, I could use any p norm for that matter, subject to the constraints that yi times a transpose xi minus b is greater than or equal to 1 minus alpha I for all I. So in formulating this particular problem, I have used some heuristic assumptions, right? There was no real need to say choose this to be norm A square. There's no real reason to choose this as A alpha j whole power p. It could be something totally different. But this seems to work well, at least in practice. So we just stick to this. Right? So maybe I'll leave it to you as a homework to actually simulate this. So try to generate points as before, but now perhaps take some points on one side to be 0 and take some points on the other side to be equal to 1, and try to find the optimizing A and B.
In case we didn't bound either alpha or the one, we let both of them be free.
Okay, you just get infinity. Yeah, you just get infinity. Yeah. So in fact, even in the previous one, if I let's suppose that where do I have this? Yeah. Yeah. If I remove this particular constraint, so I just get minus. The margin itself would be t by norm A. Yes. Yes. T by norm A. Okay. Oh, T by norm A. Sure. Then wait, it's going to be a DCP issue because you're dividing by the normal. But yeah, there could be another way. Ultimately, I want to minimize T by norm A, but potentially T by norm A. Yeah, I dropped that. You can look at a different, potentially could look at a different function, but I'm not sure that would give the same answer as this. Any other questions? Okay, so let's look at another application, uh, which is basically PCA. The problem is the following: you're given a bunch of points drawn from some distribution, and the goal is to find out along what directions, vaguely speaking, is the variation the maximum. So given the x, so in other words, uh, assuming that you have these high dimensional vectors, can all of this, is there some suitable very low dimensional subspace that captures most of the informativeness of these vectors? So effectively you don't really have access to the distribution Px, but instead you're given vectors x1, x2 up to some xn. These are samples drawn from the distribution, And effectively the first principal component is basically the point for which p transpose x, where x we assume it to be a random variable. So the expectation of this squared is the largest. So v is basically some direction, and you want to know along what direction is the inner product with x. uh, so v transpose x is basically a random variable, just the inner product of v with x. So it's it's the component of x in the direction of v, and expectation of this squared is just the variance. Of course, here we're assuming that all of these are zero mean random variables. We'll assume that both the sample mean and the true mean are both equal to 0. Any questions? So the problem is maximize expectation of v transpose x, the whole square, such that norm v equals 1. So the maximizing v is called the first principal component.
So
Yes.
the expectation is being taken after the square.
Which, no, it's taken before the squaring. So it should be expected. Sorry, okay. This is what I mean. Expectation of v transpose x the whole square.
Either expectation of
We're assuming that expectation of x is 0. So I basically have expectation of v transpose x the whole square, but I can write this as v transpose x times x transpose v. So I want to maximize this, which is expectation of v transpose x transpose times v. But of course, v now does not depend on x. So I can take, just by linearity of expectation, this is equal to v transpose expectation of x transpose times v. But what is expectation x transpose? The covariance matrix. So this is v transpose sigma V. This is the covariance matrix of X. Now, in general, you don't have the covariance matrix directly. All you're given access to is a bunch of samples, right? So you can compute the sample covariance matrix and use that as a proxy for the original covariance matrix and find the direction along which the variation is maximized. And this is particularly useful in applications where the variation is not too large. There are certain components along which there is a lot of variance, but in the rest, there is almost no variance. For example, if you looked at IID Gaussians, what would the covariance matrix look like? Yeah, so if all of them had IID components, zero mean, unit variance, then the covariance matrix would basically look like an identity matrix. If you just took a few samples drawn from a Gaussian, from an IID Gaussian distribution, then the sample covariance matrix would also be close to that of the identity matrix. Okay, so what do we know about the covariance matrix? So, okay, so before that, so let's again recall the problem. So maximize. So the goal is to maximize V transpose sigma V subject to the constraint that norm V equals 1. What do we know about the covariance matrix sigma? It's symmetric, it's positive semi-definite. And what is the maximum of V transpose sigma V subject to the constraint that norm V equal to 1? No. Yeah? No. It's the largest eigenvalue of sigma. So this is simply equal to the largest eigenvalue of sigma. And what does sigma, so what is the V star that achieves this maximum? That will be the eigenvector corresponding to the largest eigenvalue. So I'll call this the largest eigenvector, which is essentially the eigenvector corresponding to the largest eigenvalue. So the problem of finding the first principal component is basically one of finding the largest eigenvector of a positive semi-definite matrix. Now, in many cases, you want to do more. You want to not just find the largest or the first principal component, but want to find k principal components. And in that case, the problem is the following. So the goal would be to maximize the expectation of norm V transpose X, where this X is basically the random vector. And V is basically, I'm assuming that the random vector in Rn, then V would be an n by k matrix with orthonormal columns. And you can show that this basically amounts to finding the k largest eigenvectors, or the eigenvectors corresponding to the first k eigenvalues of the matrix, of the covariance matrix sigma. So, okay, that's fine. We have the following problem, but what kind of a problem is this? This convex optimization problem? Yes. No. Okay, so let's first look at the objective function. Take the simplest example. So maximize V transpose sigma V. Sigma is a symmetric positive semi-definite matrix. V transpose sigma V is a quadratic form. What is this a convex function?
Yes.
It is convex, so no issues over there. Constraints: norm V equal to 1. Does this form a convex set? It does not. So this is not a convex optimization problem. Okay, let's see if we can formulate this in a different way so that we can ultimately get a convex optimization problem. Now, there are different ways of viewing the same problem, but and one nice way to think about this is you try to approximate the positive semi-definite matrix, the covariance matrix, by a rank 1 matrix. Right? So suppose I had this norm constraint, that norm V equal to 1, then maximizing V transpose sigma V is basically equivalent to minimizing norm VV transpose minus sigma, Frobenius. If norm V is equal to 1. The reason why that holds is because the Frobenius norm is VV transpose minus sigma. This is also equal to the trace of VV transpose minus sigma transpose with VV transpose minus sigma, which is equal to the trace of VV transpose times VV transpose minus VV transpose 2 times VV transpose times sigma plus sigma transpose sigma. But this is just trace of V transpose V the whole square plus sigma square minus 2 V transpose sigma. The first one is V transpose V transpose, which is the same as the trace of V transpose V times V transpose V, just because trace of AB is equal to trace of BA. So this quantity is just V transpose V the whole square. Sigma is of course symmetric, so trace of sigma transpose sigma is the same as transpose of sigma square, trace of sigma square. And the third term is left as it is. But what is the first quantity equal to? It's 1, because we're assuming that the norm of V is equal to 1. That's important. So it is 1 plus some constant, because this is given to us, minus what is trace of V transpose sigma? V transpose sigma V. Right? So these two are anyway independent of V, and there's a negative sign in front of V transpose sigma V. So minimizing this particular Frobenius norm is the same as maximizing V transpose sigma. Yeah. Okay, so you'll see this as an equivalent formulation of the PCA problem. Right? So you can either view it as finding the maximum of V transpose sigma V, or finding the rank 1 approximation to sigma. All right, so let's try to relax this particular problem. Okay, so my goal is again to minimize this particular quantity, which is minimize V transpose minus sigma Frobenius norm, subject to the constraint that norm V equal to. This is still the problem that we have. Now let's look at V transpose. What properties does this particular matrix have? Yeah, it is rank 1. Yes. What else do we know? So let's take this particular X equal to V transpose. This has rank equal to 1. What else? Yeah. Okay, it's PSD. What else do we know? What is x times x equal to? X times x equal to x itself. So does such an operator have a name? The projection matrix. So x square equal to x. So it's a projection matrix. Okay, that's good. Anything else? So let's suppose that the variance of x is 1. So what can you say about the eigenvalues of sigma, or what can you say about the largest eigenvalue of sigma? So assume that sigma or variance of x is 1. What would be the largest eigenvalue?
Here the main PV transpose our data.
Which the original random. Okay, perhaps I should not be overusing notation. Let me call this matrix V, capital V square equal to capital V. Y. Okay. 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 I'll leave this as an exercise there. So if we sort of normalize all the vectors so that the mean is equal to 0 and the variance is equal to 1, then the largest eigenvalue will be equal to 1. Okay. So what can you say about the matrix I minus V? Yeah. Greater than or equal to, you're close, but in what sense?
Yes.
It's PSD, right? So this is greater than or equal to 0. Okay, so that is good.
I minus
I minus V. Okay, yeah, I minus sigma is greater than or equal to 0. But of course, we want a V which sort of captures this. Uh, in particular, you can also say the same of I minus V if V is the largest eigenvector of sigma. Okay, so now let's look at the following problem of minimize the Frobenius norm of V minus sigma subject to the constraints that the rank of V equals 1, V square equals V, V is positive semi-definite, and I minus V is also positive semi-definite. Is this a convex optimization problem? Why not? Okay, which equality constraint? Okay, so this is basically the same as saying v square minus v equal to 0. Okay, so let's suppose that I relax some of the constraints. In particular, I will relax this particular constraint. So what about the first constraint? Set of all matrices for which the rank is equal to 1. Does this form a convex set? Why not? Can you speak up? Yeah. Yes. Okay. Yeah. That's true. Also, I can take A and minus A. Both of them have rank 1. A minus half A plus half minus A would give me 0. Yeah. Sorry? Yeah, matrix V is small matrix. Yes. I can take the optimization variable to be small v, but there's a reason I want to keep it to be the as a, in the matrix form, and that is because I can you can use the same form for the case where I want k principal components. Uh, sure, but then I have the norm v constraint. The norm of v should be equal to 1. Yes. There's another reason why I want to keep the rank constraint. So recall that V should be a projection matrix, right? If V has to be a projection matrix, then what can you say about the eigenvalues of V? Huh? It has to be 0 or 1. Right? So, so all the eigenvalues are either 0 or 1, right? Okay, so then what is the rank equal to? Correct. So the number of I for which the eigenvalue is equal to 1, right? Okay, so rank equal to basically the multiplicity of 1. We're dealing with symmetric matrices, so they're orthogonally diagonalizable. So arithmetic multiplicity is going to be equal to the geometric multiplicity. So the rank is equal to the multiplicity of 1. But what can you say? Okay, is there an easier way of getting this in terms of the matrix sigma or V? For that? Okay, so it's equal to the multiplicity of 1, but all eigenvalues are 0 or 1. So the rank is also equal to the sum of the eigenvalues. You agree? So it's equal to the trace. Which is equal to the trace. Okay, so basically I can replace this condition with trace of v equals 1.
So do we require this I minus v greater than or equal to 0 constraint because we are relaxing the v square minus v constraint because it automatically follows.
Yes. And in fact, instead of looking at this particular objective function, I look at the trace of v transpose sigma transpose sigma times v. Using sort of the similar ideas that I had earlier. I'll write, instead of using the norm or the norm squared, I'll write this as a trace constraint, which is basically the inner product between these two.
Why did we relax?
Well, effectively, I just want to keep, I have an equality constraint, which I don't want to keep over here.
Does that not affect the answer?
As it turns out, it doesn't. Okay, so let's just do a quick test.
So where do we get the final trace or do we get that form?
There are some more steps. You can sort of simplify the original objective function, the square Frobenius norm. So let's say that I generate a bunch of random points. Five, 10, and 8, X transpose. So this is my sample covariance matrix. Okay, so in this case, there's one eigenvalue which is really large. The remaining eigenvalues are pretty small. So let me just for now normalize this matrix sigma. And so the largest eigenvalue is 1. The remaining eigenvalues are fairly small, as one would expect. and that I can print sigma. Here it's not evident just by looking at it that it's close to uh, it's not doesn't really look close to the identity matrix, but the largest eigenvalue is 1, and the eigenvector that corresponds to this is whatever this particular vector over. So if I look at E, which is the first eigenvector, the largest eigenvector, is the eigenvector times eigenvector transpose.
That is just compared.
I know, but so I'll have to reshape this. So this would be this is the true V star transpose. Right? So and now let me just try to solve the optimization problem that we have. So V is, I define a variable which is a phi cross phi matrix. Okay, and what else? An objective which is cp dot maximize, it's called sigma, sigma times sigma times V. What are my constraints? Trace of V should be equal to 1. What are the other constraints? That V should be positive semi-definite, greater than 0, and I minus V should also be positive semi-definite. Okay, there seems to be
Objective
Pathways.
sigma dot
which one?
Pathways of trace of sigma.
Ah,
sigma constant.
that's fine. Say sigma is the symmetric matrix, so I can okay, that's nice. And let's look at value minus E, and it's pretty close to 0. The values are fairly small, So this is optimal. All right. So I guess I'm out of time right now. But yeah, do experiment with this. Play around, and so I guess this kind of also ends the classes for this particular course. We'll have the final quiz or exam on Thursday in the regular slot. The exam will be here and in LH1. I'll post the sort of seating arrangement by Thursday. It will be a regular pen and paper exam, closed book, but again you'll be allowed an A4 sized sheet where you can write only on one side of the sheet. Yeah. The syllabus is everything covered up to now, but more of what has been covered after the midterm exam or after the break.
That's what two sides.
Well,
Exam on one side.
you should know the first part well enough, so the second part should be easy.
The exam is 1 hour.
It'll be for a little over an hour, not for full 1.5 hours.